Morning, students. Welcome to another session of probability and statistics for data analysis. We started this course last week. And then, give me a second. Yeah, so last week we looked at, last week was learning outcome 1. And then we looked at develop understanding of distribution theory. That was on a Saturday. And then on the Sunday, we discussed develop understanding of classical interface. So yeah, and then today we'll be looking at develop understanding of Bayesian statistics. So this is more of like mathematics and statistics in a kind of way. So yeah, let's get started. So what is the indicative content? We have Bayesian inference, statistical modeling, linear theory, approximate normality, posterior distribution. And then we have Metropolis, Hastings algorithm, slice sampling, Hamiltonian or hybrid, Monte Carlo, which is HMC. As usual, we have a video to watch. So give me a sec. Let me pull the browser up. Come here. Copy the link. And then paste it here.
Today we'll be doing a smell test. None of today's participants will have any idea of what they are smelling. Therefore, all the reactions are real. Yeah. Oh, wow. People say that the New Lynx fragrances are just as good as the high-end fragrances. So let's put that to the test.
I wasn't talking about him personally. I was talking about smell.
Crazy.
Yeah, so the video is all about Bayes theorem example, probability and statistics theory, and tutorial. So we'll be looking at it after the session. So right here we can see something like a pie chart, which has different sections. We have section 1 to 4. We have B1, B2, B3, B4, and then each of those charts have its own section, like it is color coded and everything. So that's one of the things that we'll be looking at today. So first of all, we have to know what Bayes theorem is and its use in statistics. So Bayes theorem is used to show the relationship between one condition and its inverse. So take, for example, we have P, which can be A or B, is equal to P, can be B or A. We can also say P, A, divided by PB. So which literally we can see. Give me a sec. Yeah. I see it here. I see, yeah, something related to this. So this is a clear explanation of literally what this is. So yeah, so where P, A or B is the probability of A occurring given event B has occurred. And then we have PBA, the probability of B occurring given event A has occurred. And then we have PA, the probability of event A. And then we have the probability of event B, which is PB. So, and then there's a quick note here that says event A and B are independent events. That is, the probability of the outcome of event A does not depend on the probability of the outcome of event B. So if these two events, A does not depend on it, like the outcome or the result does not depend on it. So yeah. So there's an example right here, which says, imagine you are a financial analyst at an investment bank. According to your research of publicly traded companies, which is 60% of the companies that increase their share price by more than 5%. In the last 3 years, replaced their CEOs during the period. At the same time, only 35% of the companies that did not increase their share price by more than 5% in the same period replaced their CEOs, knowing that the probability that the stock price go by more than 5% is 4%. Find the probability that the shares of a company that fires the CEO will increase by more than 5%. So the first thing you have to do is, before finding the probability, you must define the notation of the probabilities. So, which is PA, the probability that stocks increase by 5%, which is this. And that, and then PP is obviously like replacing the CEO, the probability that the CEO is replaced. And then PLB, the probability of the stock price increases by 5%, given that the CEO has been replaced. So, which can be found in one of these paragraphs. And then the last one, which is probability of the CEO replaced, given the stock price has increased by 5%. So, obviously, using the Bayes theorem, we can find the required by doing this and all. So, literally, like, this is a good example of how we can apply Bayes theorem. So, thus, the probability that the shares of a company that replace its CEO will grow by more than 5% is 6.7%. So, yeah. So in continuation, PA or B is referred to as posterior, which means the probability of occurrence of A given B. PB or A is refers to as likelihood ratio, which measures the probability given event A of occurrence of B. PA is referred to as parallel, which represents the actual probability distribution of A. So yeah, we have classification, which involves require a training data set consists of DHD, where the D are the data instance to clarify input, and the HD are the correct class label of HD, and so on. So we have an objective to predict and provide. So obviously, we have the training in this diagram, we have the training info, and then the desired target output, and then we have the input, supervised learning, and then the output. So the error is target output minus actual output. Yeah. So over here, we looked at a clear example of Bayes theorem, and then here we'll be looking at probability basics. So this is another example. We have, let A be an event on the world and B be another event. The probability that event A will occur if event B occur is called conditional probability. So yeah, so the probability of A and event A occurring and event B occurring is called conditional probability. So we have this formula here, which is usually the number of times A and B can occur, which is joint probability, divided by the number of times B can occur. So yeah, we have this formula here, yeah, which is similar to something that we have here, yeah. So yeah. Similarly, the conditional probability of event B occurring given event A has occurred. So we have this. So PBA is equal to PB and that. So hence, my bad. Let's go back. Hence PBA and A and is equal to PBA times PA. So yeah. So let us for us to actually understand it more, we can also do this. Give me a sec. So we have this sheet. So if you find it complicated to remember everything, yeah, I know that there's this sheet here. So this is complement rule, additional rule, which is union, conditional probability, and Bayes theorem. So yeah, you have dependent, interdependent, which are inclusive. So intersection, which is A intersection B. And then we have union, which is A, union B. We also have complement, which is A complement A, you understand? And then we have the mutual exclusivity, disjoint and not. So we have loads of other rules and everything, joint probability among other rules and all. So let's get back to what we are doing. Yeah, so like we saw here, we have joint probability. Let me find it. Yes, we have joint probability here. So this is also what we have, similar to what we have here. So excuse me. We have A intersection B is equal to B intersection A. Therefore, A intersection B is equal to B or A times A. So yeah, so that's it. And then to make it simple for us, we can use the Bayesian rule, which the formula we've been saying it, we've been saying it since we started this session. We also have this Bayesian classification, which is discriminative model, generative model, apply Bayesian rule, and apply the map, which is maximum posterior rule. So yeah, let us check a good example of this. Let's say I'm trying to go through this. Yeah. Just for us to understand. Okay. Yeah, we'll come back to that soon. Yeah, we have discriminative, we have generative, and then this is how we apply the Bayesian rule to both of them. And then lastly, we have applied the maximum posterior rule. So that is these are the formula of all that and all. So yeah, a popular example is play tennis. So play tennis training examples. So day one, the outlook is sunny, the temperature is obviously hot, the humidity is high, the wind is weak. So you can decide that no, you don't want to play tennis. Day two is also sunny. The temperature is hot, humidity is high, the wind is strong. So you're not playing tennis again, which is no. And then day three, you have overcast. The temperature is hot, the humidity is high, the wind is weak. So yes, you want to play tennis. And then day three, there's rain in the outlook, the temperature is mild, the humidity is high, wind is weak. Yes, so yeah, and so on and so forth from day 1 to day 14. So that's a good example of that. So yeah, with that example, we can apply the formula that we're talking about, which is Bayes theorem formula. So P, we have play, which is yes, which is 9 out of 14. So yes, if you count it, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 14, yeah, is yes. That means that yes, you are playing tennis. And then the remaining 5 is no. So which is written here. So we can do this. Play yes is sunny, because excuse me, we can also break it down into different outlook and temperature, and then the overcast and everything. So if it is sunny, how many times do we want to like play? Yeah, so if it is sunny, and then we select yes. So there's no, so sunny, outlook is sunny. Yes, we have this 1, and then we have 2, which is literally 2 out of how many yeses? 1, 2, 3, 9 yeses. So that is what it meant. And then if it is sunny, and then the play is no, so how many is that? We have 1, 2, and 3. So 3 out of 1, 2, 3, 4, 5. So that's the way it works. That's the way it works. And so on and so forth. Also, we have the overcast. So overcast is yes. And then, so how many times are we going to play if the overcast is yes? So we have yes, overcast is yes, yes, this is 1. Overcast is yes, yes, this is 2. Overcast is yes, yes, this is 3. And then 4. 4 out of 4. 4 out of the total of 9 of yeses, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is how we have 4 out of 9 here. And then how many times is no? Overcast is no. So overcast, with overcast no. I don't think we do have any overcast that is no here. So the answer is 0 out of 5. And then rain. The outlook is rain. How many times can we play? So rain, we have this, which is yes, 1. We have this, which is yes, 2. We have this, which is yes, 3. So 3 out of 9, we are. What about no? The no is just 2. So 2 out of 5. So that's the way we did that. Also, the next one is temperature. Obviously, we have the temperature section here. So how many times are we going to play the tennis if the temperature is hot? So the temperature is hot. How many times are we playing the tennis? Which is 1 and 2. So 2 out of 9, we are playing tennis. So what about no? That is 2. I think that should be 2 out of 5 too. So let us check. Yeah. So you are right, which is 2 out of 5, and so on and so forth. So we can do the same thing for mild. Also do the same thing for cool. Also, you can take this further and obviously do the humidity too. So if the humidity is high, how many times are we going to play tennis? We have this, which is 1. We also have this, which is 2. We have 2 days, and then we have 3. So 3 out of 9 days we'll be playing tennis if the humidity is high. What about, yes, 1, 2, 3. Yes. So if the humidity is high, we are going to play 3 out of 9. What about if the humidity is high? How many times I don't want to play the tennis? We have no here, which is 1. We have no here, which is 2. We have no here, which is 3. We have no here, which is 4. So 4 out of 5 times we are not playing tennis when the humidity is high. So you can do that for also do that for wind too. So that's how that is. So moving on to the next one. Yeah, so this is a breakdown of everything that I've literally just looked at here, which is a good example of what we are looking at today. So look up the lookup table achieved in learning phase. So we have outlook is sunny, the place yes, which is 2 out of 9. And then we have temperature cool, and then play yes, 3 out of 9. We have humidity high, play yes, 3 out of 9. We have wind strong, play yes, 3 out of 9. We have play yes, which is obviously which is total number of yeses that we have, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 9 out of what? 9 out of 14. So that is why we have 9 out of 14 here. So yeah, moving on. Also, we have outlook sunny. The place no. So these are the yes parts, and these are the no parts. Don't get it. Don't confuse yourself with it. If you feel like, oh yeah, it's confusing, just go back and check the table. So yeah, that will properly explain it to you. So we have the outlook, which is sunny, and the place no. So that is 3 out of 5. We've seen that here. So 3 out of 5, which is literally here. Sunny, which is 1. The first one is no. The second one is no. And then somewhere here also we have no. So how many no's do we have? We have 5 no's. 1, 2, 3, 4, 5. So sunny is 5, 3 out of 5. So that is why we have that here. And for these two, the same thing is applicable to that. and then the total number of no, which is the same thing I find the total number of yes. So in the old table, how many no's do we have? We have 1, 2, 3, 4, 5. Yeah, so that is why we have 5 out of 14 here. So it's quite easy to understand. But if you feel like, oh yeah, it's complicated, just go back to the table, break it down, look at this explanation, and yes, so you better understand it. So another explanation, we have the test phase. Yeah, given a new instance predicts its class label. So we have outlook on the X, we have outlook sunny, temperature cool, humidity high, wind strong, and then decision making with the map rule. So we have sunny, which is yes, cool too is yes, high is yes, and strong is yes. So yeah, so that is literally the number of yeses that we have, and multiply by the total number of yes. So we have, so this is it. So this 2 divided by 9, 3 divided by 9. So 2 divided by 9 multiplied by 3 divided by 9, multiplied by 3 divided by 9, multiplied by 3 divided by 9, divided by 9. I mean, like, yeah. Yes, I think it's dividing. So we divide all this, and after the answer we get, then we now multiply with this. So that will give us 0.53. That is for the yes. And then for the no, we do the same thing too. So the answer is 0.0206. So given the fact that P yes X is less than P no, we label X to be no. So that's it for the play tennis example using the Bayes theorem. So yeah, in summary of what we've looked at today, we know that Bayes rule can be turned into a classifier. Maximum A posterior, which is map, like we saw here in this. I think we saw it somewhere here. Is it here? Oh no, it's not here. I think it's somewhere. I think somewhere in one of our slides. So yeah, hypothesis estimation incorporates prior knowledge. Max likelihood doesn't. Naive Bayes classifier is a simple but effective Bayesian classifier for vector data. That is, data with several attributes that assumes that attributes are independent given the class. Bayesian classification is a generative approach to classification. So, continuation, evaluate Bayesian experimental design with appropriate example. So Bayesian experimental design is a framework that incorporates Bayesian inference principles into the process of designing experiments. It allows for the optimization of experimental designs by explicitly considering prior knowledge, certainty, and the desired goals of the study. Here is an evaluation of Bayesian experimental design with examples. So we have this. I don't think there's an example here. I think we should be able to like look for the example somewhere here. No. This is a book, or yeah, this is a journal or something like that. Yeah, if you're interested, you can obviously like have a look at that. Yeah, incorporation of prior information. One of the key strengths of Bayesian experimental design is its ability to incorporate prior knowledge into the design process. Bayesian methods allow researchers to include existing information or beliefs about the parameters of interest as prior distributions. This prior knowledge can help inform the design of the experiment by guiding the allocation of resources and sample sizes to areas where uncertainty is high or where information is lacking. For example, in clinical trials, prior knowledge about the effectiveness of a treatment can be incorporated to inform the size and allocation of treatment groups in order to optimize the study design. Also, we have adaptive designs. Bayesian experimental design also facilitates adaptive design, where the design of the experiments can be modified in response to accumulating data. As data is collected, the posterior distribution is updated, and this updated information can be used to inform subsequent decisions, such as sample size adjustments or modifications to experiment conditions. This adaptivity allows for efficient and dynamic allocation of resources, leading to more informative experiments. For instance, in drug development, an adaptive design can be used to adjust dosage levels or treatment groups based on interim results. So, yeah, if a pharmaceutical company wants to release a drug out right now or a medication out, they use adaptive design, which helps them to like adjust the level to adjust the dosage level of treatment groups based on interim results, which optimize the allocation of resources and increasing the chances of finding an effective treatment. So that is how you can do that by using adaptive, which usually means adapting. So optimization of information gain. Bayesian experimental design aims to maximize the information gained from the experiments. This is achieved by considering the expected utility or the value of the information gained. By quantifying the uncertainty in the parameters of interest through the posterior distribution, researchers can optimize the design to obtain the most informative data. For example, in market research, Bayesian experimental design can be used to optimize survey designs by selecting the most informative questions and sampling strategies to gather the most valuable information about customer preferences and behavior. That's another good example. And then we have, lastly, complex experimental design, which means Bayesian experimental design can handle complex design involving multiple factors, interactions, and constraints through the use of Bayesian computational methods such as Markov chain and Markov chain Monte Carlo, which is MCMC, sampling of approximate inference techniques. Researchers can explore a wide range of design possibilities and evaluate their performance under different scenarios. This flexibility allows for the constitution of complex experimental setups and the optimization of design that are tailored to specific research questions or hypotheses. So this brings end to our session today, and then these are the references that was used today. Yeah, we also, so if you have any question, don't forget, as usual, don't forget to like send us an email, and then thank you for coming today. Just for recap of what we did today. So this is learning outcome 3, which is develop understanding of Bayesian statistics. So we looked at what Bayesian statistics is, and then the different formula. We looked at the popular example, which is the play tennis training example, and then we're able to use the formula to find the play tennis instance and everything. And then we add the summary, and then we looked at several examples of experimental designs with Bayesian. So yeah, to conclude the class, let's get back to our video and watch the video.
Hello everyone, welcome to another session by Simplilearn. Today, we are going to discuss the Bayes theorem, an important subtopic that comes under probability theory. We'll start this video by talking about probability and conditional probability. After that, we'll move on to the Bayes theorem and understand its formula and a real-life example where the Bayes theorem can be used. So, let's get started. What is probability? Probability is the branch of mathematics concerning numerical descriptions of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking, 0 indicates the impossibility of the event and 1 indicates certainty. The higher the probability of an event, the more likely is that the event will occur. Let's look at an example. A simple example is the tossing of a fair unbiased coin. Since the coin is fair, the outcome that is heads and the tails, are both equally probable. The probability of heads equals the probability of the tails, and since no other outcomes are possible, the probability of either heads or tails can be said to be 1 by 2, which is also 50%. The probability of an event can be calculated by number of ways it can happen divided by the total number of outcomes. Now that we know about the probability, let's see if you can answer this question. What is the probability of drawing a jack and a queen consecutively from a deck of 52 cards without replacement? Here are your options. Post your answers in the comment section and let us know. Now let's move on to conditional probability. Let A and B be the two events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred and probability of B is not equal to 0 is called the conditional probability. It is denoted by PA/B. Thus, we can say that PA/B is equal to PA intersection B divided by P of B, where PA/B is the probability of occurrence of A given that B has already occurred, and PB is the probability of occurrence of B. To know more about conditional probability, you can check our previous video, which is specifically on conditional probability. Now let's move on to Bayes' theorem. The Bayes' theorem is a mathematical formula for calculating conditional probability in probability and statistics. In other words, it is used to figure out how likely an event is associated on its proximity to another. Bayes' law or Bayes' rule are the other names of this theorem. The formula for the Bayes' theorem can be written in a variety of ways. The most common version is PA/B is equal to P of B/A into P of A divided by P of B, where PA/B is the conditional probability of event A occurring given that B is true, and P, A and B of B are the probabilities of A and B occurring independently of one another. Let's solve a problem using the Bayes' theorem to understand it better. There is a cricket match tomorrow, and in recent years, it has rained only 5 days each year. Unfortunately, the meteorologist has predicted the rain for tomorrow. Now, when it rains, the meteorologist correctly forecasts rain 90% of the time, and when it doesn't rain, he incorrectly forecasts rain 10% of the time. Let's calculate what is the probability that it will rain on the match day. So, the two sample spaces here are the events that it rains and it does not rain. Additionally, a third event is also there that meteorologist predicts the rain. So the notation for these events appear below. Event A1 is equal to it rains on the match day, event A2 that it does not rain on the match day, and event B is the meteorologist predicting the rain. Now in terms of probability, we know the following. Probability of A1 is 5 by 365 that it rains 5 days in a year, which will come out to be 0.0136. PA2 is 360 by 365, that is no days for 360 days in a year, which will come out to be 0.986. PB/A1 is 0.9. This signifies when it rains, the meteorologist predicts the rain 90% of the time. In a similar manner, PB/A2 is 0.1, that it does not rain, the meteorologist predicts the rain 10% of the time. Combining all this, we can calculate PA1/B, that is the probability it will rain on the given match day, given a forecast of rain by meteorologist. The answer can be determined using the Bayes' theorem as shown below. So here's the formula of the Bayes' theorem, and putting all the values that we have calculated in the previous slide, the probability that it will rain on the match day, given a forecast of the rain by meteorologist, will come out to be 0.111, which will be equal to 11.11%. So there's an 11% chance that it will rain on the match day, given that the meteorologist has predicted the rain. I hope this example is clear to you. With this, we have come to an end of this video on the Bayes' theorem. I hope this was helpful. If you have any questions, then please put them in the comment sections. Also, if you like the video, then please subscribe to the Simplilearn channel and hit the bell icon to never miss an update. Thank you for watching and keep learning.
Hi there. If you like this video, subscribe to the Simplilearn YouTube.
So, in conclusion, we looked at develop understanding of Bayes statistics today. So tomorrow, which is learning outcome 4. I guess I'll see you tomorrow. Enjoy the rest of your day.